Good to go.
All right, you can see my screen okay and my laser pointer?
Yeah.
Yes.
All right, sounds good. So I guess this is the last lecture of the class. Well done, and sorry in advance, but hopefully it'll be at least a little bit fun. This will be one of those where hopefully you just sit back and absorb it without being too deep of a group of thinkers. What I wanted to share here was kind of a perspective on as you move forward and you start incorporating satellite data into your everyday lives. You know, how do you make choices about using the right ones? Or if you're really ambitious, building new ones, because it isn't as easy as it sounds, but it's very rewarding. So I hope this works. We have what's called a mission systems engineer, this great guy on the PACE project, and every mission has one of these. This is an engineer that has kind of elevated to the top of their discipline, and they get responsibility for understanding how everything works because they're on the hook for all the engineering aspects of the mission, including putting all the pieces together. So we spend a lot of time trying to fill him in on what the science capabilities are and how they relate to engineering. And the guy is so creative that he decided to outline it on a whiteboard and create a little movie that describes his understanding of the state of ocean color science. So I'm going to hit play and voice over it, and I hope that it works. So we're starting in the sun, hydrogen, helium, making photons bouncing around in the big star. Let me know if this is not playing. Okay, great. Photons escape the sun, coronas, ejection, and they start finding their way towards Earth. These happy little photons somehow find their way into the Earth's atmosphere, bounce off of clouds. If they're so lucky, find their way to the ocean's surface. After which, if they penetrate the ocean surface, they bounce around, hitting phytoplankton and CDOM, and make their way back up through the atmosphere into the field of view of the spacecraft instrument. In the guts of the instrument, there are optics. The photons continue to bounce around. They can convert into counts, split onto different detectors, and find themselves in data control units and data handlers and things that create files where they're then beamed through Ka and X-band transmission down to Earth, collected in disks for a ground station, which then uploads all the bits into a cloud where they become files and they get to a mission operations center, where the files are then sent to a science data system where algorithms are cranked, geophysical products are made. They're given to the community to start coming up with amazing ideas, which will hopefully all become your PhDs. So there you go. That is the entire discipline of NASA's satellite ocean color engineering, from the sun down to your brains and your degrees, coming from our mission systems engineer. So hope you enjoyed that. All right, why are we including this talk? More specifically than what I said before, I predict that greater than half of you are going to A, use satellite data for your research. And I really hope if you do, you understand your engineering choices. You will probably be asked at some point to serve as members of space agency science definition teams or National Academy teams, or different kinds of organizations that are expected to come up with ideas for the future. I really hope that you get to serve on proposal panels and satellite mission review boards. Those are excellent ways to learn how the sausage gets made. And really, the holy grail would be you write proposals for your own new missions and get something on orbit that's an idea of your own. So with that in mind, I wanted to give you a little bit of the basics of what's going on and how you start making some of these informed decisions. First half of this will just be a description of satellite ocean color and some questions and answers that I'll probably just do one way to avoid trying to do question and answer over Zoom. The second half is going to be a case study. All right, so normally at this point, we would start a discussion where I'm standing in front of a whiteboard and really begin it with, hey, you probably have figured out by now, just in playing with a little bit of satellite data, that these instruments come in all shapes and sizes, and they all have different kinds of capabilities, whether it's something for atmospheric correction, or something in the optics or the wavelength selection or what have you. So how do you actually choose what to use and build? What I'd like to do next is actually punt it back to you and say, given this case study, let's spend 10 minutes on a whiteboard and you tell me what you think this kind of mission would look like. And this is not a single satellite per se. This is a mission to monitor coastal harmful algal blooms, just as an experiment. What we do is we go around the rooms and you all would chime in, and it usually is a lot of fun. At least it's a lot of fun for me. And I'd ask you the questions in white and you'd say things in green. So I'd ask you, what kind of measurements and data products do you want? And then all the voices would chime in all at once. And it turns out you want all the data products possible. What instruments do you want? Active instruments like LiDARs, passive instruments? You want both of them. You can't decide. You need them both. What wavelengths do you want?
All of them.
Yeah. Do you want to go into thermal bands so you can do SST? Inevitably, yes. What resolution? Less than a nanometer hyperspectral, of course. Across UV to shortwave infrared. What spatial footprint do you want? Smaller is always better here. Can you get better than 10 meters? Okay. What repeatability? Well, if we can't see the globe every day, what are we doing here? Phytoplankton or transient? Okay. How good do you want your imagery to be? Super high SNR, because we always talk in the space of SNR here, and I don't want any image artifacts. None of those stripes I see in these imagery. What temporal stability? Well, change is bad. All right, so we'd have this conversation, and right now, normally the whiteboard would be filled up, and if I had had more time, then we'd put dollars on it, and cents and powers and things like that, and then ultimately, I'd look you in the eye and say, you can't have this mission, not from orbit alone. You have neither the budget to do it nor the technology to do it. And frankly, half of what you asked for in the design conflicts with what's technologically possible. So that's when everybody gets sad. And then we start talking a little bit more about why you shouldn't be sad, because technology is changing and you are all brilliant. And then we reach the conclusion that compromises can be made depending on your overarching science objective. So what do I mean before I leave this screen on the compromises? Well, for one, global repeatability and spatial footprint are totally at odds with each other right now, at least from a single satellite instrument. If you've noticed, if you looked at Landsat or MSI and Sentinel-2, these are instruments that have very narrow swaths because they have very, very small spatial footprints, 10 to 30 meters. But the downside of all of this is the way they have to be built to do this with their narrow swath is a singular instrument typically doesn't see the same piece of Earth for another 14 to 16 days. Now you can overcome this by having multiple in orbit. The Europeans have shown that 2 of them can reduce this repeatability to about 5 days, which is fantastic. If you want to have global one-day coverage, well, you need a very wide swath instrument. And you can't have wide swath and small pixels in a photon limited system. So that's why missions like MODIS and VIIRS and what PACE will be like can do global work, but they're going to be at 1 kilometer. The reason for this, again, is photon limitation, so forth. So you can't have them both, not right now anyway. Oops, wrong way. Here's where cost comes in. And of course, cost is the obvious one. Yeah, every instrument is expensive. They're just getting more expensive in some cases, cheaper in other expenses and so forth. But if you have a limited budget, and I'm talking a limited budget of like $1 billion, we're not saying, you have 500 million, 200 million, and you have to do things. These are these big enterprise classes that are multiple billions of dollars. The other problems with this is they compete for each other in engineering space too. An active sensor like a LiDAR is a power hog, and it wants to have a really low orbit to reduce some of that. Passive remote sensing, you want to have an orbit that's much, much higher. You can see more of the globe that way. So when you start getting into the builds, now you have to think about, well, how much power can I actually put into these instruments? And what do my solar panels now need to look like? And how do I position them into the sun the right way and so forth? But we found even through like the PACE experience and MODIS and CWIS and others before us, that even when you're talking about a singular instrument, things get really difficult and very expensive very fast. Thermal bands, as you might imagine, need to be super cooled. So they're big instruments at microwave wavelengths that need massive temperature control. So they're really their own separate instrument. The same is almost true for shortwave infrared bands as well. So now you have ultraviolet to near infrared, where you can kind of operate at medium temperatures on orbit, but you have these other very specialized bands that need to be super cold as well. And that increase, whether you know it or not, increases size, because now you need thermal shields and you need to have cooling system and heat loop pipes and things like that. So all of these things fight with each other. And then when you get into capabilities, well, it might sound easy to say, I want more wavelengths because I know what a spectrograph is, and a fine spectral resolution going from 10 nanometers to 5 nanometers to 2.5, whatever it is. Well, every time you make these kinds of steps, you're again competing for photons. And when you do that, your image quality degrades accordingly. So nothing to be sad about, just want you to understand the landscape here in the choices that you're making. So let's back way up a little bit and just talk about high level stuff. What kind of choices do you have in terms of some general spacecraft and instrument design? And we'll start with push broom versus whisk broom. And whisk broom is a scanner in this context. I took this from a nice book from Seeley Martin, if you're interested. Easiest way to think of a push broom is a two-dimensional type CCD array like you would have in your cell phone. And just imagine that that is flying along track. There are no moving parts. It's just continually collecting pictures. But you have many detectors to do that. There is no singular detector that's capturing everything on Earth. It's a grid of detectors that are moving forward. So the advantage of this is you can move slower, which means you can collect more photons. The disadvantage is every little detector is a slightly different little instrument. And you'll see evidence of what I mean by this later. So you have a bunch of little instruments you need to intercalibrate. Now, the whisk broom or the scanner is something that actually rotates or goes back and forth. And the advantage of doing something like this is you can reduce the number of detectors that you have. In fact, the CWIFs only had one. And OCI for PACE is being designed in a way so that there's a virtual singular detector. So you get past all of these striping issues and little detector differences. But since you're spinning and moving, you are spending much less time actually looking at Earth, which reduces the number of photons you're going to take in. So two different choices there with some examples for you. Now, the other choice you might have to make if you're designing from the scratch is what orbit you want to go to. Geostationary versus low Earth orbit, LEO. Let's be new if this, nope, that's, come on now. And let me get rid of my pointer and see if I can. All right, there we go. Hopefully this is playing for you. All right, great. So geostationary, the design is such that you position the spacecraft very far out. They're 36,000 kilometers. And its orbit actually tracks the orbit, the rotation of the Earth, so that it's constantly looking at the same place. You use this for cell phone technology, GPS, so forth, and the weather service satellites all operate like this. The advantage, of course, is that you're staring and dwelling at one particular place, and so that you can actually see change, which can be very powerful if that's what you're looking for. Disadvantage of this, of course, is that you're only seeing certain parts of the globe. So you need a network of this. And right now, there is no network of ocean-colored geostationary instruments. There is talk of new geostationary instruments. In fact, I believe there's a European one. The Koreans have been doing this for a while. And NOAA in the US is building something called GeoXO, which, if done properly, will have a sustainable network of ocean color from orbit. There's also a new mission called Glimmer coming up. Our group is responsible with some PIs from the University of New Hampshire to do some proof of concept. So it's there, and it's going to be amazing, but it is very different than low Earth orbit. This is low Earth orbit. Effectively, what you're looking at in this case is a satellite that is going pole to pole in an ascending orbit. Dark crosses down, descending through the backside of the Earth, and then ascends from the southern pole to the North Pole and the sunlit side of the Earth. Advantage of this is, like we were talking about, you can see the entire globe. The disadvantage of this is, well, it's a cloud, and if you can hear my dog being a monkey, I'm really sorry. It was just a path. The disadvantage of this, of course, is it's a cloudy Earth. And so if you miss one day's view of that part of the Earth you're interested in, chances are you're not going to see it unless you see it with another satellite. So you have a consumer's market rates now, and the best resource I can think of to point you to is the IOCCG website, really easy to find. And under one of their tabs, they talk about all the different ocean color satellites that they have. And they're stratifying up by past missions, current missions, and future missions. So what you're looking at here are current and future missions. And you can study this a lot later, but what I wanted to call your attention to is the information in the light blue box in the center here. Just scan really quickly and you can see the differences in swath sizes, which would indicate global repeatability or not. You typically will need to be 1,500 kilometers to 2,000 kilometers wide to be a global mission in the sense of 1 or 2 day coverage. Spectral resolution is all over the board. The number of wavelengths or bands that they have is all over the board. And their spatial resolution varies greatly. And that's not just for the current missions, for the ones they have planned now. So there's a lot going on, and there's going to be a lot to choose from, and you want to be smart about this. So how to choose? Well, I am paid big bucks to be biased about one particular mission. I am a fan of a lot of them, but in the context of showing you why a mission like PACE got designed the way it was, I thought I'd step you through the process of all of that. And of course, I obviously know it better than I know the other ones. This is just a one-slide primer in case you've heard me say PACE 1,000 times already, but you don't actually know what it is, and that's totally okay. Still love you. Hopefully you do know that NASA has a 40-year record of Earth observing satellites that have continually been building on top of each other. Technologies get better, or they continue heritage missions and build cookie cutters and so forth. But the goal is to have major investment in long-term sustained Earth observing. The PACE mission is a little amazing and difficult and weird all at the same time because it's multidisciplinary. And we'll get to why it's difficult yet amazing in the next slide. But it's for ocean biology and biogeochemistry. It's to do atmospheric aerosols. It's designed to study clouds. And even though it is a coarse footprint, will be used to study land as well. That's actually a lot to ask of one mission. It has 3 instruments. Its primary one is the ocean color instrument, which is like the super cleverest name of all, even though it does cloud and aerosol science too. That's being built at Goddard. And it's the only required instrument on the payload. We're fortunate enough to have 2 contributed multi-angle polarimeters. I think you talked about polarimetry previously in the class. That's wonderful. This is a way to do it from space while studying polarimetry at different viewing angles, where ocean color instruments typically only have 1. These are contributions from Maryland and from a consortium in the Netherlands, and they're really CubeSat sized, being bolted onto the spacecraft. So think of a box of tissues, and that's roughly the size of those 2 polarimeters. Now, a mission like this, or really any mission that at all, including one that you might propose, even though it's only been real life for 6 years, it's practically old enough to drink. Missions like these really begin their conception when the latest mission is launched. So in the case of PACE, right after CEWIS was launched in 97 and MODIS Terra was launched in 99, folks started using them. And you realize how amazing they are. You realize what you can be successful with using their data products. And then you tend to realize what you can't do. And that's when you begin the process of thinking, well, how do I fill these gaps? And so over the course of the next decade and a half, what became PACE evolved slowly over time as different opportunities arose and so forth. But it was really 15 years later before the mission became real and was directed to a center to build. You know, the legacy, CEWIS was Veers. For polarimetry, it's Poulter and Miser if you're interested. And if you care about such things, some key characteristics, we're about 2.5 years out from launch. That seems like forever, but it's not, given that the instruments aren't fully built yet. It's one of the rare Earth science missions that's going to get launched out of the Cape Canaveral from Kennedy Space Center on a pre-owned Falcon 9, actually. We are not getting a new one. We are getting a slightly loved one. The good thing about that is it's less expensive and it's tried and true. Like most LEO instruments, it's roughly 700-kilometer altitude. This is LEO, so it's polar, ascending, and sun synchronous. And what sun synchronous means is that it's always looking at the same place on Earth at the same time of day every day. So our equatorial crossing is 1 p.m. But that means every day it will cross the equator at 1 p.m. But wherever you return home to, if you look up at 1 p.m., it may be flying over you, independent of the latitude that you're at. All right, so let's get into how one goes into designing the instrument system for a mission in real life. Well, you start with science objectives. Now, remember, we had 15 years to really cull these, consolidate them, and put them into what became a science definition team report. It is precisely 308 pages. So read the executive summary, but the details I will leave up to you. What it distills down to is we have four major overarching science objectives here. The first is just to extend ocean, aerosol, and cloud climate data records. That means build on the legacy of CWIS, MODIS, and VIIRS and keep doing the same thing. Don't let that legacy die. But because this is a new mission, and as it stands right now, it's a one-off, do more innovative things as well. Make new global measurements of ocean color that you need to better beat down all of the uncertainties and the lack of understanding that's critical for things like the IPCC report that came out 3 days ago. Go on and collect global advanced observations of aerosol and cloud properties, again, focusing on uncertainties, but do things better than we've done before. And then the real trick is tying this all together. If you're familiar with MODIS and VIIRS, you are aware that they have cloud disciplines and land disciplines. In fact, we talked about this yesterday, but unusually the way those teams were set up is they don't spend as much time as one would think actually interacting and building up science capabilities in concert with one another. And the challenge that we actually got from headquarters in the community was you build ocean capabilities while talking to the atmospheric folks and vice versa, so that we can start understanding for really one of the first times how oceans influence atmospheres and vice versa. Now, the trick with that is it makes it a lot harder to build a mission that can do everything. So to talk about all of the challenges that we have for all these things, I have two images here that really represent to me everything that's difficult in ocean color and atmospheric remote sensing. So on the left, you're looking at Northern Arabian Sea, and on the right, you're looking at the north coast of Libya. So back to the left, let's just walk through this really quickly. Of course, the promise of pace is getting to different algal groups, right? So primary thing number one, but we don't want to confound our interpretation of phytoplankton community structure with image artifacts. So image stripes can become a problem there. And as we'll talk about a little later, sun glint is a really big problem too, just like clouds. You can't see through it. For atmospheric correction, as you learned from Kurt, absorbing aerosols are a problem. We haven't really solved them yet. And then the biggest trick for doing ocean color well, when you have to do other things on top of it, is somehow figure out how to build a system that can handle a very, very dark ocean adjacent to very, very bright land and bright clouds. And that requires a really high dynamic range of response. So if you move on to the right side here, Libya, this actually is really more confounding than it appears at first blush. So again, you have varied contrasts, and this is not between land, ocean, and clouds, but in the two different dust plumes that are going offshore too. I can tell you, if you actually look at geophysical products that come out of NASA right now, they can't tell those two plumes apart through modeling, even though you can look at them and see that they're different. Because they're different, they have varied optical properties. Well, how do we handle that? The biggest problem and one of the biggest contributors to uncertainties in these big IPCC reports is that there's a very limited understanding at this point how aerosols and clouds interact. And that is challenged in part because they all have varying altitudes. Sometimes you have aerosols above clouds, sometimes you have them below clouds, sometimes you have aerosols above dust plumes, sometimes you don't. It's a big problem when trying to tease out how you're going to do this and how to build a system to overcome it. So that's when we start with requirements. You start thinking like that thought exercise that we just did. What do you do next? How do you build a system that can address all of these problems while still addressing all of these goals? Well, first you get to ground surface distance, GSD. In this case, we cannot be any bigger than 1 kilometer because that's what Heritage is doing. So if we want to continue our climate data record, then we need to be 1 kilometer or better. Well, if you really want to get to different algal groups, as we spoke about yesterday, you need an instrument that can go beyond the spectral characteristics of Heritage. So let's get hyperspectral instrument that runs from ultraviolet to the near infrared at least 5 nanometer spectral steps. Well, if you really, really want to start helping out aerosol community, you need to bring, if you see down here, that ultraviolet down into 320 nanometers. Get as short as you possibly can. That becomes a problem because ultraviolet technology is very different than visible technology. The coatings are different, the efficiencies are different, so you have to make some choices about what you care about more. To do aerosol research, you need shortwave infrared bands. To do ocean color well, you would also want them. Now, sun glints, we haven't spent a lot of time talking about this other than the atmospheric correction problem, but one way to mitigate it is simply to look away from it, to tilt your instrument. In this case, as you're ascending up towards the subsolar point, you simply have your instrument looking away from it. And then as you cross the subsolar point, you tilt your instrument forward so that you're looking, again, away from the sun glint. And think about how you might have seen some of this last time you were in an airplane looking out the window. And on one side of the plane, you can see the sun reflecting into your window. On the other side of the plane, you cannot. The instrument wants to behave very similarly. Instrument performance requirements drive just about the rest. If you want to have good climate data records, then you need really stable instruments that do not degrade on decadal lengths. And space is a harsh environment, so that's a tough call. So you need calibrations. Ocean color uses the moon and the sun for this. And then in our case, we added multi-angle polarimetry to fill in some of the gaps with our aerosols and some of our hydrosol remote sensing as well. So the point I want you to take here is this is kind of a ground up problem, just like a hypothesis that you're trying to develop. You build the instrument system up around the problems you're trying to solve. As you can see already, certain choices were made. This is not a small GSD instrument platform. We had to give something up. But what you end up with is something that looks like this. This big behemoth on the side is the next generation ocean color instrument. Down here in the lower left-hand corner, you can see how big it is for scale. It is reminiscent of a riding lawnmower in terms of its size. Imagine what it takes to tilt an instrument of that size. You know, people would often say, well, C was tilted. And you're like, yeah, that was like 35 kilograms. This is 300 kilograms. It's a lot of mass to throw around, and it's a big center of gravity to maintain stable. But we did end up with a hyperspectral scanning radiometer that does span from the ultraviolet to the near infrared. We were actually able to reduce it to 2.5 nanometer spectral steps, although the full width half max resolution is still 5 nanometers wide. You can see there are swirl bands, daily global coverage, it tilts, and so on. So a design concept can be realized. What were the challenges that we had to deal with after we made some of these decisions? So we talked about atmospheric correction in V2. Kurt did an amazing job of that. We touched on conscientious use of data yesterday. And what I want to do today is just briefly have a conversation, and it won't be a long one because everybody's tired, on why our decisions were made, why we chose to tilt the instrument, and give you some real, you saw that cute picture of the Arabian Sea. Now we're going to actually get down into the details. Whew. All right, sun glint. So what you're looking at up here, you've seen before on the left-hand side, where this is a model simulation of a polar orbiter that does tilt on the top panel, 20 degrees fore and aft, and does not tilt in the bottom panel. We saw this in Kurt's lecture a week and a half ago. Anything that has color in here is data that is not usable. So you can see that when you do tilt, you shrink the geographic range of unusable data. And you can see this in real data too. Sorry. You can see a sea-whisk orbit where there is tilt happening. And as we discussed in Kurt's lecture, that pattern is smaller, but you still lose a little extra. That's that horizontal stuff. This is actually where the region of tilt is happening. And it's, of course, on the same day, and they have different, one's descending and one's ascending orbits, meaning they're going in different directions. But this is same day par. You can see that the non-tilting instrument loses a fair amount of extra information you might want. Well, let's try to quantify that. So this is the kind of exercise you would go through in a design study. And there are 3 pieces of information here. On the x-axis, you have the tilt angle, because you can ask the question, why do I have to tilt to 20 degrees? Wouldn't it be better to tilt to 40 degrees or 10 degrees? How do I know? On your y-axis is the coverage lost as a function of how long it takes to tilt. So in a perfect world, you would have an instrument that tilted instantaneously. It took no time whatsoever to go from fore to aft. But we know that's not perfect, and that would still lose some data. So that's what, but for information's sake, that 0 seconds line is included here. But let's just take a look now at tilt angle. We chose 20 degrees for our sea-whisk and for OCI. Let's talk about time now. Well, if you could tilt fore and aft, and it only took you 20 seconds, you're only talking about losing roughly 5% of your data. If you triple that to 60 seconds, now you're losing roughly 7% of your data. So you can play these games. So now we're talking about a 300 kilogram thing, and swinging it back and forth is an engineering challenge. What we ended up settling on was we have 60 seconds that we can use that will not substantially disrupt the spacecraft and the other instruments. But if you follow that on this axis, you can now see, well, look, if we want to make it even easy on ourselves and we only use a tilt angle of 10 degrees, well, crap, now we've lost 9% of our potential coverage. Whereas if you go really, 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 really wide, well, of course, that number starts going down. You could get down to 5 and 4 again if you really have view angles that are, or tilt angles that are big. What problem do you think you're going to have in ocean color if you start having these extreme viewing angles? Your atmospheric correction becomes much, much harder. So there's a real crazy sweet spot in here. Just to put this in geographic perspective, to put some numbers on these, we went through a study where for solstices and equinoxes, we evaluated the extent of loss due to sun glint for ocean-only pixels. So there's a latitudinal dependence because there's far more land in the northern hemisphere than the southern hemisphere. So what you're looking at here is the percent data loss. And in this case, for this particular example, for this summer solstice, you know, if you don't tilt at all for every swath, you're going to lose roughly 9% of your data. And the range of your loss goes from into the southern hemisphere pretty far north. And this is really talking about 42 million kilometers of ground pixel on Earth. If you can shrink that, well, all of these numbers reduce, and these percentages actually result in a delta that is not insubstantial. And so just to frame this into context, the difference here of 17,000 kilometers square is roughly the size of South America. So it's a substantial amount of data loss if you don't do something like this. And that is, frankly, how we won this fight, because you go to these review boards who are thinking about, this is an engineering challenge, it's going to cost money, it's going to cost time, it's a moving part. You know what engineers hate on spacecraft? Moving parts. If nothing moves, they're happy. And we're asking them to build something that not only swings back and forth, but spins. They really don't care for us. But you can finally convince them when you talk like this, holy crap, this is a lot of real estate to not be looking at. So anyway, just for context, the summer solstice is the best case scenario. All of this actually gets worse if you look at some of the autumn equinoxes. All right, moving on to image and artifact design. Now, explained to you before that there's the difference between this push broom and this whisk broom capability. Here's an example of that. You have a paper from Schweiman Hu in 2012, which is a really nice exploration of all of this. You're looking at chlorophyll, I believe it's in the South Pacific somewhere, and it is the same day, same time of day look from CWIFS, which is a rotating telescope with one of those one science detectors, versus MARIS, which is multiple science detectors. Okay, and you can see a difference in the homogeneity of the images. For one, there are a lot more speckles and push brooms. For two, push broom instruments are not wide swath by nature. So to overcome that and create a wide swath out of them, what you can do is have multiple of them that look in different directions on the same satellite platform. And what you're seeing here, this unrealistic vertical scene in the ocean, is where one camera stops and the next camera begins. So there are image artifacts throughout MARIS and CWIFS. And this isn't knocking MARIS or lauding CWIFS. This is just to illustrate to you there are differences. And all multiple detector systems like push brooms, or even multiple detector scanners like VIIRS, have stripes and ocean color imagery because it's a very, very, very dark ocean. So in HICO, you can see that there are stripes because of the CCD array. In VIIRS, you can see there are stripes because they have multiple detectors on their scanner. To give you a sense how this trickles down into geophysical variables, we conducted another study. This top row is basically a simulation of a push broom image for a uniform ocean with just a small 0.1% miscalibration error, which is not so bad actually, but you can see the stripes that would be realized and they're fairly realistic. And if you look at this transect at pixel number 100, you can see that in a water leaving reflectance at 400 nanometers, there is 0.002 wiggle in the that particular band. If you take averages here and you look at the full spectrum, you can see, of course, this varies by signal strength. So there is somewhere less than 10% error across the spectrum that you might see introduced by your choice of instrument here. If you start adding random noise, the point here is that it grows. So we had a science requirement to have as little image striping as possible. And that forced our hand into going to like a CWIFS-like design. Now, all that said, the difference between CWIFS is that in these scanners, 1 kilometer instrument. Here at MARIS, you can do 300 kilometers. You do Landsat or MSI and Sentinel-2, you can get down to 30. So if what you're interested in can tolerate these stripes, you're not making a wrong choice by using them. You just need to understand what you're trying to study. Then last, and this should not be a surprise to anybody, it is a quantum leap to move from multispectral radiometry to spectroscopy. The left-hand side, you can see the band placement over the colors of the rainbow for our heritage instruments. For PACE, you can see that it's going to be a continuous rainbow right in the middle. And how I've had to go to management and sell this, because again, it's a lot easier to build another CWIFS than it is to build PACE, is try to explain to the head shed that we cannot do phytoplankton community composition if we continue on with our heritage type instruments. And so just picking back on the Arabian Sea for the umpteenth time, Colin mentioned these Magdaluca, which were taking over a previously diatom dominated system. Well, what do you see spectrally when you look at them? Well, in the middle panel here, this is an emulation of what VIIRS would see. In the red dots, you're looking at the normalized light absorption for Noctiluca. And for the black dots, you have the diatoms, okay? And what has been very convincing to others is this lack of information content. There is only one unique wavelength here to actually tell you anything about the differences between these two species. If you have a hyperspectral instrument like OCI, suddenly you can really fill in a lot of these gaps between wavelengths, and suddenly, you know, it's like putting on your glasses. Principle, there's far more information, and hopefully you brilliant people can go off and do something with it after it launches. So the end product becomes something that looks like this. Those are the two little polarimeters that went by. That is a meteoroid shield. Actually, OCI trails behind. Let's see if I can pause it. Those are the two polarimeters that just swung by. I'm sorry, I don't even know what you're looking at. But there you go. This video is online, and I'm happy to walk you through it. All right. So before we move on to our last little chapter here, I just want to say that there is something really, really satisfying about looking at these fine spatial footprint instruments. Seahawk, Hawkeye instrument on the Seahawk CubeSat. This is the difference between a retrieval, I believe, or in Monterey Bay, chlorophyll, of what you would get from a 100-meter instrument versus a 1 kilometer, 1,000-meter instrument. And yeah, you can see the image striping in here, but I don't know, it is still a beautiful image in its own right. And I don't know if you follow like at NASA Oceans, but on Twitter, Instagram, Facebook, and so forth, but there's a ton of imagery going out. And lately, a lot of it has been coming from Landsat and OLI because it is just gorgeous. And what I wanted to demonstrate here is, this is from a paper Brian France wrote in 2015, is how many unique, interesting little features in a 30-meter Landsat pixel actually fit into a 1 kilometer MODIS image. So there you go, trade-offs. Be a good consumer. All right, then I'm going to conclude with something that Kurt did a brilliant job helping me work through. We're going to call it chasing photons, and then I'm going to let you go. This is considerations for making and maintaining useful satellite ocean color measurements. This is a more mathematical description of the trade space you're going to work in when you picked out what kind of instrument you want, and then you scratch your head going, well, why can't I have hyperspectral 1 meter data? This has been transposed into a chapter on the Ocean Optics webbook. So I won't spend a lot of time on the math of the equations because you can read about it in nauseating detail at your own pace when you get home. All right, so the question we have is, why don't all ocean color satellites measure hyperspectral radiances at meter scales? So let's do 3 quick case studies. A stationary instrument, like a geostaring, at a 1 square meter patch of Earth for 1 second. The second one is we'll start moving that like a Earth observing LEO instrument. And then we'll go into the CWIS OCI type instrument, which you're scanning side to side. What I want to hopefully impart to you very quickly is we can actually count the number of photons that leave this patch of ocean. We can see how many of them actually make it into the detector system of the satellite instrument. And then we'll explore how many photons actually have to reach this instrument to get a meaningful SNR. So for your reference later, there's a bunch of geometry that we have to take in consideration, and that is all in this figure here. There are also another number of characteristics that we need to consider. Don't sweat too much of this now. When the optical efficiencies, the quantum efficiency, slant range, altitude, aperture, these are all things that are engineering choices in the detector system. And the values that we're using here are pretty typical ones. We're going to focus on a fluorescence channel, so 678 nanometers, and have it be 10 nanometers wide. A typical radiance at the top of the atmosphere before atmospheric correction is listed here, 14.5 watts per square meter per micron per steradian. And what we want for mission length pace, which really needs good fluorescence bands, is a signal to noise ratio of roughly 2000. So that's our benchmark, fluorescence in a red band at 2000. This has been a massive headache. When I'm talking about simple SNR here, just for completeness, this is a massive oversimplification because it's not including a bunch of things, but we're really talking about the number of electrons over the square root of the number of electrons. All right, so right now, again, all the units are here, all the numbers are here. You can recreate this on your own. The end result on the left-hand side is the power reaching a detector for a 1 square meter aerial footprint viewed for 1 second. Number of photoelectrons, 3,812 under this scenario, at the top of the atmosphere. So we're interested in performance at the bottom of the atmosphere, right? So if we consider that in this part of the spectrum, the ocean contributes roughly 5% of the signal, then the number of photoelectrons from the ocean surface actually reaching the detector is roughly 190. Not a whole lot. That SNR results in roughly 62. So we're nowhere near where we need to be. This is an instrument that actually gets to stare for a whole second, and a whole second is a lot. So the integration time would have to be raised to 8 minutes to actually get to 1400 just for. So it seems like 1 second is a lot. 8 minutes is impossible. You can't dwell and not wiggle on orbit enough to look at 1 meter patch for 8 solid minutes. So that's just something that we got to take off the table. We can't do this right now. All right, so let's talk about a satellite that moves and stares at this 1 square meter patch at nadir, just looking straight down like a push broom doing its thing. So now we have to add a velocity term, but you'll note the integration time has reduced from 1 second to a very, very, very small fraction of a second. So you repeat the calculations with the new integration time, and you find that you get less than 1 photoelectron reaching the detector from the ocean surface. The SNR is less than 1 in this case, and no, there's no way you can sell a mission on this. That's not going to happen. What happens if you increase this pixel size to 1 square kilometer? The integration time increases by 3 orders of magnitude, and the area increases by 6 orders of magnitude. Redo all of the math, and now suddenly you're getting 28 million photoelectrons at your detector. This is why we increase our footprint. Now the SNR is off the charts, way more than you need, far more than you need. So now you can start scaling back from 1 kilometer to something smaller. This is why Landsat is what it is, and MSI, HICO, all of these other instruments. You are in a photon-rich system with this kind of instrument. Bush brooms are very attractive because of that. In this case, you could still get to almost 3,000 SNR with a 250 meter pixel. But you suffer from image quality problems. So let's look at the CWIFs and PACE OCI instance where you have a moving satellite that is scanning. This case, okay, what I just said. In this case, you have a field of view you have to take into account. You have a swath with, let's say, roughly radians translating into 1,400 pixels. You do a little math here and divide the 28 million photoelectrons by pixels, but remember, it's 1 detector measuring all these pixels, and that leaves roughly 20,000 photoelectrons from the ocean surface reaching the detector. All that said, you're not looking at the full time you're scanning. The useful duty cycle is really 1/3. Otherwise, you're looking at the back of the instrument. So you're really talking about 6,000 ocean surface photons. Propagating this to the top of the atmosphere at roughly 120,000, and your SNR has reduced from what you saw before to 350. Still far less than we want. So now you start having the questions with your science team saying, all right, what can we do with 350 SNR? Is this good enough for applications that we have in the near infrared? Well, if you want to get up to the original values of the 2000 target, well, you need 16 times this, which is why in a science definition team report for PACE, the requirements table is listed for this wavelength, for the conditions that we're talking about, 678 nanometers, 10 nanometers wide, 2000 SNR. The requirement on the system does this at 4 kilometers. Again, this is all part of the trade space. To get to 2000, you have to build up something. So in our case for PACE, we are actually, the engineers got clever and we reduced the dynamic range, basically conceding that these bands can do nothing for clouds anymore. And we have an SNR that's approaching a little over 1200 for a 1 kilometer pixel. But again, it was an engineering choice. We had to give something up. In this case, it was the spectral range is going to not work for another discipline, which is a big thing. Okay, I'm done with the busy part of this lecture. If there are questions, I'd love to take them, but since this is, until tomorrow, this is the last time I'm probably on screen for more than 10 seconds. Just wanted to leave you with 2 things, 2 words really about what I hope you will take with you on your career. 2 things that have been meaningful for me. And the first is to persevere. Everybody gets bad paper reviews. Everybody gets proposals declined. Everybody has lousy coworkers. You find ways to put on a smile and you move forward and your successes will be even that greater. PACE itself got canceled by our previous White House administration for 4 straight years in a row. And as you might imagine, that's a pretty tough morale problem when you're a staff of like 600 working on a mission. But we persevered. And one of the funniest things that actually came out of this, which is for the Star Trek fans, is our visualization studio decided to have a little fun at the expense of the, at the time, very, very popular Space Force that was emerging. And they came up with this. So this is how your tax dollars were spent while we were canceled. So yes, we're safe from the birds of prey. The second is collaborate as much as you can. I wouldn't even be in this room talking to you if I hadn't, collaborated with all the excellent instructors and, really been so enriched by them in various different ways, so much so that, they're friends and collaborators, good friends. There's even interesting ways to do this in pandemic. And one of the funniest ones, again, just to share an anecdote, was like everybody else in the world, 3 or 4 months into shutdown and quarantine, people baked, right? And there became a little rivalry between Goddard and headquarters to see who could bake the prettiest, most extravagant things. And we started sharing these on Twitter and Instagram under the hashtag NASA Bake Off. That picked up so that our counterpart, European Space Agency, decided they wanted in. And then it became, a religious thing where the two space agencies were trying to outbake each other. This was my contribution. It's a sweet potato galette, but I was really bored one night and decided to acknowledge the collaboration. So I don't know if you could read it, but it says ESA and NASA. So that won for a little while, and then they got clever and started building cakes that looked like instruments and things like that. But nevertheless, the point is we got through it together through collaboration. This poor little guy collaborated with me last time in a much, much different way, but I do appreciate his sacrifice and his enthusiasm for our mission. So that's the last thing I got. It's been a pleasure talking one way to you guys. I'm here for questions. I know you probably have a crap ton of work to do for your projects, so I'm going to stop. I seem to have lost audio too.
I was just going to make a comment really quick while people are formulating questions. That 4 years of canceling the program was really a tough time for all of the scientists and engineers involved. And Jeremy, I just can't tell you how amazing it was to have you come to these meetings and stand up and say, that's okay, don't worry, we're going to persevere and we'll get through this. And if it doesn't get through this administration, we'll get it through the next administration. And if not that, we'll just keep going. And your positivity and your can-do attitude is really inspiring and really helped people get through these times when they thought that like maybe everything they had done was for naught. And so when he talks about perseverance, like, he knows what he's talking about. So like, thank you for that, because we're almost there.
We're almost there. No, well, thanks for hanging with us and for the kind words.
Who's ready to build their first satellite?
Any other questions I can answer at this point? You ready to go home?
I have a question regarding the figure you showed that was tilt angle versus pixels lost or area lost, or I'm sorry.
Let me see if I can find it for you.
Yeah, so there was right at 7% of the area lost, you had a line drawn horizontally across. I was curious as to whether that was, right there, some sort of target that you were reaching regardless of the tilt angle.
Yes, exactly. Awesome observation. One of my hardest lessons when I started working for PACE was that scientists and engineers speak wildly different languages, at least conversationally. We work in the same units, but they aren't interested in me standing on the top of the mountain and just spouting off ideas. They want science translated into numbers. And what I mean by that is they need something they can test. Like, we can declare success if we use a statistic that proves our hypothesis, right or wrong. An engineer building something like this only declares success when they meet what's called a requirement. And the requirements have to be numerical, something they can go in and actually say, I can build this, I can verify that this will do this for 10,000 orbits. And so that 7% line became the requirement for all of this. And that's why we put it in there for our study, because it basically confirmed that if we had a 20-degree instrument tilting instrument, we had 60 seconds plus a little slack to actually tilt it back and forth. So long answer, but a great question. You need, there are other positions within a flight project, and if you ever start building your own, you want to recruit them earlier. They're called instrument scientists, and they're effectively the Rosetta Stone. They are someone who may not know everything about the science you're doing or everything about the engineering, but they're excellent translators. So when an engineer comes and says, hey, this one little tiny part amongst 6,000 parts isn't working right, this person can say, well, okay, I think that'll have a 0.015% impact, after scratching their head a little, then they can come back to me and say, can you handle a 1.05% impact? And then we make a decision and go forward. Make friends with a couple engineers when you build these things before you actually submit the proposal. You're small again, so I can't see you. Just yell anything out you'd like.
I just have a question about signal to noise. What do you guys usually aim for when you're looking at that?
Can you ask that one more time? Signal to noise, and then I lost you.
Oh, I'm like screaming over here.
All right.
What signal to noise do you guys usually aim for? Or were you in pace?
It's a good question. I'm sorry I don't have that slide handy. So really, your requirement for signal to noise depends on what you're trying to study geophysically. And so in the case of trying to do some kind of derivative analysis or inversion algorithm to come up with some metric of phytoplankton community composition, we did the sensitivity studies to come out, well, how big does your signal to noise actually have to be? And it turns out that it's actually spectrally dependent. So in our case, it turned out that it was roughly 2,000 in the blue and green bands, went down to roughly 1,000, a little less in the red bands, and then it gets even much, much lower in the shortwave infrared bands. But it kind of follows roughly like one of those aerosol curves you saw in Kurt's lecture, kind of a smoothly varying power law can describe it. And when you think about it, that kind of follows what you'd see in the bright ocean too, a lot of blue light, a little less red light, and so forth. And it's weird how atmospheric correction plays into this as well, because you can make sacrifices in ranges in the red that don't use it. So for example, you might want a ton of blue and green light because you want to study photoprotective pigments that fall somewhere in there. You don't really need a whole lot of red, except for the bands you're doing atmospheric correction with. So again, I don't do short answers, but it's kind of not a one size fits all. But for the sake of this, let's go with, here, I will show, at the end of the exercise, actually had the table. Sorry. There we go. This was the table on the right here was what the science definition team report suggested to us. We have spent years scratching our heads and sharpening our pencils and come up with much better values. And it turns out your ultraviolet can't get much better than 300 in that part of the spectrum. We can overperform and frankly need up to 2,000 in the blue. The red was pretty much, a little more aggressive than it needed to be here and so forth. But again, if you're studying land, you don't need these that high because you have a lot of signal already. Cloud folks don't need this either.
That's kind of a piggyback question off of Sarah's. You had some numbers showing that with 1 kilometer resolution, you're looking at something like 23,000 SNR, but when you go down to 250 meters, you go, I think you had 2,300 or something like that. So that to me looks like there's some sort of non-linearity in that function. I was wondering if that's a simple exponential, or is there a lot more going on to that function that's causing that?
It varies by the square root of the number of pixels in the denominator. That's all. So like if you, a 1 kilometer SNR would reduce by if you were comparing a 1 kilometer and a 500 kilometer, sorry, a 1 kilometer and a 500 meter instrument, so your 1 pixel versus 4 pixel, the SNR would scale by the square root of 4. So it'd basically be SNR of 1/2 for each of those 4 500 pixels. And then you could keep playing that game as you add more pixels to your box.
Got it. Thank you.
Yep. Awesome.
Thank you, Jeremy.
Sure thing. Lovely to see you all again.
Looking forward to seeing you soon.
In person.
In person would be great. Would be great. I look forward to it someday. Someday soon, I hope. Yeah. All right. Well, I'll let you get to your studies then and sign off. So cheers all. Bye.
So if we get back together at 4 for we can talk about ethics and.
Articles that might be useful to brought, not required. But you're just